Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you're shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeter is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. So these are the appropriate questions appearing in the VTU question paper. Explain the constant field, constant voltage scaling models with a diagram and scaling effect table. So the diagram and the tables will represent the answer for this question, which can fetch you 6 marks. Derive the scaling parameter for the device parameter, parasitic capacitance, channel resistance and gate delay. Already I have shown you. You can just refer back to your notes. Next, define scaling. Explain the scaling factors for device parameters. Same thing. So yeah, the same questions repeats again and again. What is the parameter for gate capacitance, gate area, saturation current, saturation channel resistance, operating frequency? Each one of them, 8 are there. Each may be fetching you 1 marks. Separately 6 marks, so almost it is equivalent to 1.5 marks for each of these answers. So if you refer back, you can get an idea about all these things which has been discussed. So we have seen the short channel effects. The electron mobility varies, and as a result the whole length also is going to change because it is reduced. So this is how the current would look. So the channel effective length would be reduced due to the shortening of the channel, and therefore the current flow also varies, and the current flow is given in this kind of an expression, which is with respect to the saturation current. So if you simplify and remove of the integrals, finally you will be left out with this expression. So the current expression also changes when you are considering the short channel effect. So as I have told, the mobility varies. So in MOS, short channel MOS transistor, mobility varies because of the carrier velocity in the channel is going to vary because of the reduced length. So as a whole, the bulk mobility is going to vary, and it is given by this expression. Therefore, the dependence of the surface electron mobility on the vertical electric field can be expressed by this formula, where mu n is the mobility of the electrons. It is given by mu n naught 1 plus theta ex, and this is the expression which varies, or which is with respect to the mobility of the charge carriers. This whole thing is further simplified. And what exactly is the representation for mu n naught? It is the low field surface electron mobility, and theta is called as the empirical factor. So once you simplify this, it can be given by mu n naught 1 plus eta into VGS minus VT, where all these expressions are considered as standards or can be neglected, and the whole final expression is like this, where eta is called as the empirical coefficient. So whenever the short channel is considered, the length varies, as a result the mobility varies, as a result the current varies, and the whole of the electric field is going to change. That in turn has an impact on the mobility and the current flow. So next we consider the modification of the threshold voltage. Yes, I have not told you this. The one more parameter which is going to change is the threshold voltage. So threshold voltage is varied because of the short channel effects. And before understanding what is the threshold voltage for the short channel effects, we need to understand the threshold voltage for the long channel effect. So normally, since we have so far not discussed, so first we will consider what is long channel effect, or normally what is the threshold voltage of a MOSFET, and then we focus on the short channel. So this is the expression for the short channel. Before we understand, we will go along with what exactly is, this is the expression for the long channel. So what exactly is this expression? We will try to have a correlation and try to understand the reference of what exactly the threshold voltage is. Normally in a transistor, the channel formed is assumed to be rectangular. That means the length is L and the width is W. But when short channel, you have the two terminals, drain and the source, and there is depletion occurring, and this depletion is resulting the change in the threshold voltage. So how it is going to vary, we will see this. So short channel transistor is threshold voltage is given by this. We will focus about this later on. As I told you, first we will understand what is the short channel. But first we will understand what is the long channel. As I have told you, VT naught for the short channel is given as VT naught minus delta VT naught. So VT naught is the zero bias threshold voltage, which is meant for the conventional long channel, and delta V naught is the difference or the voltage shift due to the short channel effect. So this is how it is given. We will focus on this later. So what is the threshold voltage? The threshold voltage parameters which are reliable are the work function difference between the gate and the channel. So the focus on first understanding the threshold voltage is it is dependent on the work difference between the gate and the channel. Because channel is nothing but your diffusion material, either N type or P type, and gate is made up of polysilicon. Next, it depends on the gate voltage component to change the surface potential. So VGS, that is also responsible, because based on this the surface potential is going to vary. Next is the gate voltage component, which is reliable to create an offset in the depletion region charge. So depending on the amount of the gate voltage, the offset of the depletion region is totally dependent, and that is what we need to focus on, VGS. Next is the voltage component, which is very much necessary to have a fixed charge in the gate oxide, QOX. So gate oxide is nothing but the oxide, and there you need to have sufficient voltage in order to have the fixed charges. So charge is given by capital Q, and this appropriate term for a whole of this is capital QOX. So the analysis is basically focused on N-channel device, and obviously it is very much adaptable for P-channel devices as well. So as I told, work function difference phi GC, where G is the gate and C is the channel. So the work function difference between the gate and the channel is given, and this is how it is. So one is your gate and the other one is your channel. So depending on what type of gate material you are using. Earlier days we had metal used for the gate, but it is only nowadays we have the polysilicon. So if it is polysilicon, what exactly is the appropriate terminology you have to substitute. If it is for metal, you have to have it as a metal. So phi GC is nothing but the channel and the gate. So the channel is obviously given because since the channel is inside the substrate is considered. So the first component of the threshold voltage is the voltage drop across the MOS. The second component is the gate voltage. We have seen there just now in the previous slide. So that applied gate voltage, which is very much sufficient to achieve surface inversion. So please remember, we had three modes of operation. The first one was accumulation mode, second one was inversion mode, and next we had saturation mode. So accumulation, depending on the gate voltage, the charges are just deposited on the surface, and the moment you give the drain voltage along with a slightly greater gate voltage, some kind of inversion occurs. So charges are getting attracted and like charges will get repelled. Unlike charges attract, like charges repel, and that is how the inversion layer is created. So that is the requirement which is called as VGS. So please remember, sometime back I have told you VGS should be greater than the threshold voltage. If that is the case, it is going to happen. Next is about Q, the depletion region charge, which is due to the fixed acceptor ions located in the depletion region near the surface. So calculate the depletion region charge, which is given by phi s into minus is equal to minus of phi fixed charge. So yes, fixed charge is given by capital Q, which is given by this formula, and if you substitute in XD is the depth of the junction. So this turns out to be the bulk charge in the depletion region given by minus root of 2q Na epsilon Si mod of minus 2 phi f. So these derivations are beyond the scope. You can just try to remember these expressions. So sometimes we have seen to it that the substrate is always connected to ground. This is done in order to eliminate the effect of body, or in other words to overcome the body effect, or whatever the junctions are being formed in the substrate are responsible for the leakage current. So to overcome that, the body is always grounded. Therefore, it is neutralized, and as a result the junctions are not created. What in spite of that, in case there is a possibility that the substrate is biased at the voltage level than the source. So normally we should consider the effects of the substrate bias, which is considered as VSB. You can't neglect that, because in spite of that grounding, there may be a possibility of the substrate bias being formed or voltage existing at the substrate. So to be on a safer side, the substrate bias is also considered. Then in that case, the bulk charge at the depletion is dependent on the substrate bias, which is given as minus of root of 2q into Na into epsilon Si of 2 phi f plus VSB. So VSB is the substrate bias voltage. If it is not there, then we call it as zero substrate bias. Then in that case, the threshold voltage would be given like this. So for non-zero substrate bias, the depletion charge density term must be modified, and that has an dependency on the expression. So finally, Vt naught is given by phi Gc minus 2 Fc minus Qb. Because of that, Qb is replaced by Qb. Qb naught is replaced by Qb. This is how we have the expression. Only in case of substrate bias. Alright, yes, this is where we have the substrate bias. So that in turn is equal to this. Equate both the equations. So finally, this is what is the expression. And we have been coming across this term called as phi f. Phi f is the Fermi potential. So normally it is negative for NMOS and positive for PMOS. And similarly, the depletion region charge densities QB naught and QB are negative in NMOS and positive in PMOS. Similarly, the substrate bias coefficient gamma is positive in NMOS, negative in PMOS. So these are the terminologies which we need to remember. Obviously, most of the contents in is negative and positive in NMOS and PMOS. They are complementary. At least one, if you remember, the other can be recalled. So we will now solve a problem finding out the threshold voltage with the parameters given as substrate bias equal to 0, doping density Na is 10 power 16, polysilicon doping density is Nd, thickness of the oxide is 500 angstroms, oxide interface is NOx. So calculate the Fermi potentials. So Fermi potential for the substrate is given by this formula, Kt by Q into ln of Ni by Na. Kt is the Boltzmann constant, capital T is 300 degrees Kelvin. At that particular temperature we are considering. Q is the electron charge 1.6 into 10 power minus 19. Ni is the doping for pure semiconductor, which is given as 1.45 into 10 power 10. Capital Na already given in the question, doping concentration of the substrate 10 power 16. So if you check out, phi f happens to be minus 0.35 for this. So already we told, since this is N N type of a device, you will have negative. So Fermi potential of a polysilicon is assumed. Polysilicon is nothing but your gate. So the Fermi potential is assumed to be 0.55 volts. Therefore, we have to find out the VGC. VGC is the difference between the gate and the channel. So gate is your polysilicon as given to you already as 0.55, and the substrate we have just now calculated, it is minus 0.35. Therefore, if you check, it happens to be minus 0.90. So 5GC we have got, we have to substitute this in the threshold voltage expression. Similarly, we have to find out the depletion charge. So there are the charge at the depletion region. So this is given by the formula minus square root of 2q Na epsilon Si minus 2 phi f. So 2, and the charge of the electron is 1.6 into 10 power minus 19. Na is 10 power 16 as given in the problem. Epsilon Si is that particular silicon material into the permittivity of free space. So 11.7 is the permittivity of silicon. That has to be multiplied by epsilon naught permittivity of free space given as 8.85 into 10 power minus 14. Phi f we have found out to be minus 0.35. That is multiplied 2 times, that is given as minus 2 into 0.35. That happens to be minus 4.82. So we have found out the depletion region charge. Next, oxide interface charge Q, capital Q OX. That is given by Q in lowercase q into NOx. Q is the electron charge into whatever is the NOx. As given in the problem, it was 4 into 10 power 10, happens to be this much. Next, we have to find out gate oxide capacitance COX. It is given by epsilon OX by TOX. So epsilon OX, again, it is nothing but the permittivity of the oxide 3.97 into the permittivity of free space 8.85 into 10 power minus 14. Substitute them. TOX is given as 500 angstrom units. So 500 into 10 power minus 8. Most of the time students make mistake when they are substituting the powers and converting them either in the centimeter format or in the meter format. So that is the problem, you have to focus on that. Otherwise, for each and everybody, if you are not properly focusing and converting the proper unit dimensions, then the answers are going to vary. So the COX has been found out to be 7.03 into 10 power minus 8 farad per centimeter square. So formula for Vt naught was 5Gc minus 2 phi f substrate minus Qb naught by COX minus QOX by COX. Appropriately substitute the formulas and Vt naught is found out to be minus 0.40. So this is the long channel effect. If VSB is not equal to 0, then the formula differs. The threshold voltage would definitely be different. So for that we have to find out first the substrate bias coefficient gamma. So gamma is given by this formula. You turn out to be, happens to be 0.82. If the substrate bias is given and it is assumed to vary from 0 to 5 volts, then the formula changes. Please notice here gamma we have already found out. So the 2 phi f, all the while we considered only 2 phi f. Now we have to consider VSB also. So VSB is considered to be 0 to 5 volts. For simple reasons, if you take it as 2.5 volts, mid of it, then the threshold voltage is going to vary. By how much? It is seen that the threshold voltage variation is about 1.3 volts over this range. So whatever you have got, 0.40 you have got, right? That plus 1.3. So that much big it is going to vary, and definitely that is going to cause serious problems, because appropriate threshold voltage is considered and only that is helping us to go ahead. So just wanted to show the difference of understanding what is the long channel threshold effect and what is the formula and what is the value by considering a proper problem. Number one case. Second case, we have also assumed the substrate bias. By having an appropriate substrate bias, the voltage of the threshold is going to vary by 1.5 times. So that difference I wanted to show, and that is what has been shown now.